In an IR spectrum, the scale sort of goes backwards again because it's in wave number. I guess it's the inverse of actual wavelength. Back long ago, the spectrum used to have wavelength on the lower axis, but doing it that way tends to emphasize the wrong thing. It's an inverse scale, and the wrong area is spread out. So normally the IR that are run are linear in wave number, so about 500 on the right, way over to 4,000 on the left. We can sort of break the spectrum up into four major regions as we're looking at it. The small atoms vibrating, okay, bonds to hydrogen, right, are usually faster than 3,000, so 3 to 4,000. The larger atoms, the fastest vibration, are the triple bonds, then the double bonds, then everything else in the fingerprint region. This is all the single bonding, COs and CCs and all that, all kinds of stuff. So I mentioned that above 3,000 we can see bonds to H. We can also determine the hybridization of CH bonds, and we'll see that in a moment. That gives us more structural information. Between 15 and 2000 are the double bonds. The carbonyl absorbance around 1700 is oftentimes one of the most useful features of an IR spectrum. You can tell just by glancing at an IR spectrum whether or not there is a carbonyl in your molecule. And the fingerprint region, a lot like a mass spectrum's fragmentation pattern, that can be used to positively identify a substance by comparing it with a known. There are often going to be dozens and dozens of peaks of absorbances within the fingerprint region, and nobody can identify all of them. It's often very complex. There might be one or two that we can pick out if we have an idea what the molecule is, but the main purpose of the fingerprint region would be to match known substances because of that. So